In this video, we're going to be looking at graphing of kinematics equations, or quantities rather, position, velocity, and acceleration. But really, this is about more than just being able to graph these functions. This is about knowing what these values mean. So we need to start very basically here. Position, I think you probably have a pretty good understanding of position. The only thing that's like a location. The only thing that might be a little different in physics from what you could be used to from outside of physics is we always put a number with position. So if we're thinking about motion in one direction, I'll just say, hey, so there's some position 0 over here, and then here's a position of 1, and then here's a position of 2, and here's a position of 3. We might use units with that, 1 meter, 2 meters, 3 meters, to specify that further. We also could say, if here's a position of 0, then here's a position of 1, and then over here would be a position of -1. So we certainly could have a negative sign with our position, and that's just going to tell us, well, it's the opposite direction from 0 as the positive one, or the positive numbers were. Velocity is the rate at which position changes. Okay, so velocity is a rate. Oops, change my pen settings here. There we go. Rate of position change. And so anytime we talk about rates, that's how quickly something changes over time. So velocity is how rapidly position changes over time. So if you move from one place to another very quickly, very rapidly, then you have a high velocity. And if you do that more slowly, then you have a lower velocity. Velocity, just like position, can be positive or negative. So if we have a positive velocity, that would be a velocity in one direction. A negative velocity would be a velocity in the opposite direction. And then acceleration is another rate, but this is the rate at which velocity changes. Okay, so we change from going pretty slow to going a little bit faster. If we do that very quickly in a short amount of time, then acceleration is pretty large. If we do that in a long amount of time, then acceleration is pretty small. Now, acceleration can be positive or negative as well, and it's a little tougher to see here. The general rule is that if velocity and acceleration have the same sign, then this means the object is speeding up. So if we have a velocity in the positive direction and an acceleration in the positive direction, the object is speeding up. If velocity and A have opposite signs, one's positive and one's negative, then that corresponds with slowing down. So if velocity is in the positive direction, acceleration is in the negative, or vice versa, that object is slowing down. Its velocity is getting closer and closer to 0. Now, in terms of graphing these quantities and the relationships that we need to know there, our simplest graphs are going to be the position versus time graphs, or at least the easiest to understand graphs, I think, are position versus time graphs. We usually use an X for position. So that graph on the y-axis is going to show where that object is, and the x-axis is going to show at what time the object is at that location. So as our object changes position, we'll see the y value change, and that'll happen over some period of time. So we're going to be moving to the right on the t-axis, on the time axis here. So here the y value is equal to position. The slope, which is how rapidly the y value changes compared to the x value, or here how rapidly the x changes relative to t, or the position relative to the time, well, that's just the rate that position changes. So that's equal to the velocity. And then we're also going to look at the area under the curve. Here, this doesn't actually give us any information that we'll be dealing with in this class. So we'll come back to that later on with our next graph. Velocity versus time shows how fast and in which direction our object is moving at each moment in time. So anytime we have a positive y value, our object is moving in the positive direction. A negative y value means we have an object moving in the negative direction. So the y value here is velocity. The slope of this, that's how rapidly velocity changes with respect to time. Well, that was the definition for acceleration. And then the area under this curve, that's going to be the velocity. If we draw this curve out, the area underneath would be the velocity times the amount of time. So velocity is the rate at which position changes times the time over which that position is changing. That's going to give us just how much the position has changed. That's our value we call delta x. So if we know where the object started and we figure out how much the object's position changed, we can figure out where the object ended. And then acceleration versus time. The y value here is going to be acceleration. The slope would represent a quantity that we call jerk, but we aren't going to deal with that at this level. Once we get into problems with that, the math just gets too complex to do without some calculus and differential equations, things like that. So we're not going to do any situations where acceleration is changing. We have to worry about jerk, but the area underneath this curve, so acceleration is the rate at which velocity changes times the amount of time over which that velocity is changing. That's just going to give us how much the velocity changes, or the change in velocity, delta v. So again, if we know the velocity the object started at, we can calculate the change in velocity for this thing, so we can figure out the velocity the object ends at. So let's get a little practice going between these different types of graphs. So we'll start with position versus time graph. That'll be in the black here. So those are already laid out. I'll do the velocity in red for each of these, so we'll start over here. For this segment right here, I see that the slope, which is going to be equal to the velocity, the slope is a constant positive value. Now, I don't have any scales on here, so I don't really know where on the y-axis to make my velocity, but that's okay. We can just kind of make up some numbers here. So we have a velocity that's constant for that little section, a constant positive value. For this section, there's a slope of 0. That's a horizontal line. Horizontal lines have the slope of 0. So our acceleration is going to be 0 for that time interval. And then here, see, we have a negative slope, and that one is steeper than this section was. Steeper in the negative direction than this one was in the positive direction. So that means we have a negative velocity that's faster than this velocity was. So I'm going to go down further. Whoops, not that far. Go down a little bit further for this section of the graph. Now this might look a little weird that the velocity just jumps instantaneously, and it is a little weird. That doesn't happen in reality. So this is a simplified case that doesn't reflect a real object. We have to change velocity gradually over time. And then if we look at acceleration on this, we have a constant velocity for a little while here, so acceleration is 0 for that segment. Oops. Acceleration is 0. Then we have a jump, and that's an instantaneous jump, so our acceleration there would have to be infinite. So that's why that can't happen. But once we get past this little sharp point, we get back to a constant slope, so a constant velocity of 0. So acceleration is 0 again, because velocity is constant. And then another instantaneous jump, so we can't really show that on the graph. And then this straight line had a constant slope, so a constant velocity. So again, no change in velocity means acceleration is 0. So the acceleration graph on this one doesn't really give us a lot of information about the situation because we had that unrealistic situation. Back to red, we'll look at velocity on the second graph here. I see that on this one, the position function, it starts out with a slope that's basically 0 at the beginning. It's basically a horizontal line to begin with, and gradually this thing starts to point downward, so it gets a negative slope, and that slope gets bigger and bigger in the negative direction. It's getting steeper and steeper here. So we start out with a velocity of 0, so we need to start right here on the y-axis for velocity, and then we need to get toward bigger and bigger negative values. Now, the exact shape of this we can't really tell from the sketch, but in this class we're always going to work with constant acceleration cases. So that means velocity is going to change at a constant rate, so we'll have a straight line going downward, going down and to the right there. And then acceleration is the slope of this line, the slope of the red line. So acceleration then is going to be, well, the slope here is negative, and since it's a straight line, we'll have a constant negative value for the slope, which means a constant negative value for the acceleration. Something like that. On our next graph, velocity versus time. For the first segment here, we start out with a positive velocity, and it's a pretty large positive velocity to begin with, and then gradually that velocity gets slower and slower and slower until here we get to a velocity of 0. So for my x direction, I know I have to start out with a positive slope. I don't really know where on the x-axis to start, so I can just say, we start at 0. So we start out with a large positive slope. At some point here, velocity goes to 0, so we need to have a 0 slope right there. So we can just kind of fill in a curve here. A gradually changing slope is a curve. There we go. And then our slope begins to, or our velocity begins to get negative, more and more negative, so the slope needs to do the same here. So it gets a little bit negative, and then more, and more, and more, and more. And it just gets steeper, and steeper, and steeper, all the way down to the bottom. And then acceleration here is going to be the slope of our velocity line. This is a straight line, so it's a constant slope. It's got a negative slope because it's pointing downwards, so the acceleration will just be a constant, a constant negative value. Something like that. And then over to the next one. We start off with a velocity of 0 here, and velocity gradually increases. So in the x graph, we need to start with a slope of 0 and get to a larger and larger slope. So we have a curve upward, something like that. And they don't have to, in fact, let me change this so it doesn't end like that. Upward like that, okay. For this section, we have a constant velocity, which means the x part is going to have a constant slope. So let me get my straight line tool. Constant slope for that section. There we go. And then for the next section, here to here, our slope starts as positive, starts going up and to the right like this, gradually gets smaller and smaller and smaller until we get to a slope of 0. So we have another curve here that needs to be horizontal right there. And then our velocity goes negative, so our slope needs to go negative as well. It needs to get more and more negative right up until about there, corresponding with this point here. And after this we have a constant negative velocity, so we need a constant negative slope for the last section there. Straight line. And then for acceleration, looks like our velocity starts off with a positive slope, so we'll have positive acceleration for a little bit there. That a straight line, and it's constant acceleration. Then our velocity stays constant for a while, so velocity isn't changing. That means acceleration is 0. This has a slope of 0, so acceleration is 0. This line has a negative slope, looks like maybe a little steeper than the first line, so we'll draw that down like this. And then back to a velocity of that's constant, so acceleration has to go back to 0. Last one, starting with acceleration. So let's do velocity first. Velocity is going to be we think of it as the area under the curve here, but acceleration is a constant positive value. So acceleration tells us how much velocity changes. Velocity is going to change at a constant rate and get more and more positive for the first graph, the entirety of the first graph. So it'll be something like this. Okay, and then on our graph of position, the position graph, we use the velocity to figure out what the slope was. So here our velocity started at 0, and I don't really have any reason for starting it at 0 there. It doesn't have to start at 0. You'd really need more information about the situation to know for sure. But it's convenient to start at 0, so why not? So for our position graph, we need to start with a slope of 0 because the velocity is 0, and the slope gradually needs to get bigger and bigger and bigger, more and more positive. And again, I don't know where to start my x graph here, so I'm going to start it down low just so I have lots of room to work up here. So we start with a slope of 0, and gradually we need to curve upward more and more and more and more and more, steeper and steeper the whole way out. Over to this graph, we have acceleration that isn't a constant value here, so this one is definitely a tricky problem. Probably one that is more advanced than most of the assumptions we're going to make on these. But we can still set up general shapes for the graph here. So our velocity needs to start out with a negative slope because acceleration starts out negative. So our velocity we know is going to be becoming more and more negative, and then that slope needs to get closer and closer to 0. So I start out with a negative slope here, and then at some point I need to have a slope of 0 on the velocity. And again, I don't really know where to make these lines. I'm just going to show the general shape here. So our slope becomes gradually closer and closer to 0. We get to a horizontal line at the very end there. Now this velocity graph again could be shifted in either direction. The starting point and ending point could be changed, but what we need to show here is that the velocity starts out with a negative slope, a pretty big negative slope, and then gradually gets closer and closer to a 0 slope to match this 0 acceleration. Now switching over to position. The way I have this drawn, position needs to start out with a positive slope because we start out with a positive velocity. So I'll start position down here, positive slope, and a pretty large positive slope, and then gradually that slope needs to decrease here until this point I still have a positive slope, but much, much smaller. So I need to curve, 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 and end up with a smaller positive velocity, so it's not as steep of a curve there. Now the exact shapes here are a little tough to tell from the graph. We can't really do a perfect job of that, but all we're looking for is general trends. When we have acceleration that starts out as a big negative number and ends up at 0, velocity needs to start with a big negative slope and end at 0. When velocity starts at a large positive number, ends at a smaller positive number, acceleration needs to start with a large positive slope and end with a small positive slope. That's the kind of information that we need to be able to show on these graphs, and that's, like I said, really a lot more than just graphing. It's having a very deep and thorough understanding of what acceleration and velocity and position all mean and how they relate to each other.